So for everybody who's logged in early here, do bring up your chat window. In your chat window, there's a link to the binder demo. We probably asked you not to spin it up during the webinar, but it's certainly there for you to play with after the webinar. And the binder link is also in the announcement for the webinar as well. So if you don't grab it immediately, you can grab it out of there. And of course, all the announcements that go to SIG also go to our new SIG forum. So if you haven't logged in and signed up for our SIG forum, please do so, and you'll find the link in there as well. So we have actually a good-sized prompt crowd, and I know Louis and Ben will have a lot to show us and a lot of really, really interesting good stuff. So we're just going to go ahead and get started. And I would like to welcome all of you and thank you for joining us for our first webinar of 2019. Today's webinar, like all webinars, is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, the best way to communicate is through the chat window. So please bring that up. During the Q&A session at the end of the talk, please either indicate in the chat window that you have a question or turn on your microphone and video. Today's webinar speakers are Ben Mather and Louis Moresi. Ben Mather received his PhD from the University of Melbourne and is currently a computational geophysicist at Sydney Informatics Hub at the University of Sydney. He's the developer of the code Quagmire, which is an embodiment of his interest in thermochemical properties of the lithosphere in open source software. Our other speaker today is Louis Moresi. He received his PhD from Oxford University and is currently the chair of Earth Sciences, School of Earth Sciences, University of Melbourne. His career has been multi-continental as he further developed his expertise in computational mathematics and modeling as applied to geodynamics. You may know him as the master of the Underworld, and today both he and Ben will be telling us more about their Quagmire and their introduction to the code. So Louis and Ben, the screen is all yours.
Okay, thank you very much. I'll just check that I'm at the right level. Yeah, I'm going to go to the introduction. Ben is actually sat next to me here, so certainly for the Q&A part, we'll try and negotiate the questions as to who's the best person to speak. But I want to first give you an overview of the sort of the strategy that we have for this code and why we've done it at all, and some of the underlying things. I am going to also do the tutorial material, and that's what Lorraine was mentioning, available on Binder at the moment. It shouldn't matter how many people to that, because it's just a flexible public resource, but it's not a powerful one. So expect people to be doing these demonstrations live. If I just show you how to start it and then run through some others. Okay, so is Quagmire at all? And what is it not? Quagmire, we view it as being a toolkit for exploring large-scale dynamic models, surface process modifications to topography. What does that really mean? Well, it's like a landscape of evolution from code, but actually much in the same way that Underworld is. It's not really that does one thing. It's a whole collection of functionality that you can put together to do properly involved modifying topography dynamically, and it's based upon PET-C, and it uses PET-C for pi to make it, and we'll say trivially parallel, but maybe is the wrong story, and it's based upon using the recent PET-C EM structures, which we don't know. That doesn't really matter. It's just basically the current PET-C implements data management. It's also based on our spherical and flat triangulation code called Pi, which you can download and install through pip. And then for that, it's really just a whole bunch of operators and objects that you can to do your own kinds of landscape modification.
So Louis, you're still echoing actually pretty bad. If you can check once more your connections and any extra mics in the room are turned off. That would be helpful.
I have not, everything is on mute.
Should maybe use your laptop instead of the audio for this one.
Okay, you're on mute right now.
Okay, are you able to hear me?
Yes.
Okay, so it seems to be quite well, tightly.
Yeah.
Is that any better? And, again. Okay. Okay, so yeah, I'll just talk about. Tell me if that's better.
No, it's still echoing. Are you in the right connection? Did you try the other mic? Yeah, because you have two going.
Yeah, let me try that actually. Let me see if it's picking the wrong one. Be this one.
Yeah.
Okay, so go to Zoom. Okay, is that any better?
That's better. It's a little bit fainter, so we're not sure where it's picking it up, but that's much better than the echo.
Okay, let me. Well, I can always talk louder.
Yeah, that's great. This is much
Okay.
better.
All right.
Thank you.
We shall start again. All right. Well, I won't start again, but I will move on to. I will move on to the philosophy of Quagmire, and everyone's putting their thumbs up in the room, so that they're obviously hearing better too. Okay, so the goal, as I sort of mentioned, was to provide a bunch of Python classes that people can use to implement their favorite landscape evolution model. So this is really trying to step out of what could be quite a heated discussion quite quickly about what is the best way to implement or which pieces to put into any given landscape evolution model. And there are many different kinds of codes out there and many different algorithms. So the idea being, well, okay, we'll let people make up their own minds about what they want to implement, just make it possible for them to do that. Let people in the community define their own version of the problem and support that. And also the usual open source, open community based on tools, and that people can just use also open source and therefore leverage a great deal of the functionality, and to put in straightforward interoperability with things like Underworld. I say that it's installable through things like pip. That might not be strictly true at the moment because there's a whole bunch of stuff. There's so many dependencies that we don't really trust that. And the easiest way to do it is therefore using Docker. Okay, that's working. So there is a live demonstration running right now, and I was going to try and show you what happens when you do this. It's running on Binder, which is a free resource for notebooks running running in the cloud, and ours are based on our Docker container that you can, Docker image that you can also download. But if you click on that, it will go, and you'll see this as flagged that you get a scary-looking not found error, which is really just to do with the fact that there is no default notebook sitting in the Docker image, and that can take a few minutes. But when it comes up, it will come up with what is on the right-hand side of my screen here, running locally. There we are. So this on the left-hand side of the screen is running on Binder. Will probably be a bit slow. that's on the right-hand side of my screen, which I was intending to use for demonstrations, is running locally on Docker through just doing a Docker search for the Quagmire images. All right, so anybody who wants to try and follow along is more than welcome to try and start Binder as I just did. You will see some initial errors, but afterwards you should be in the startup page and you can immediately start navigating to other pages that are in the demonstration, as can I. These ones, I should just point out that when you land in these notebooks, they are not really running, and so they will all need to be run, and will just say restart and run everything for the time being whenever you come to these notebooks. And the reason for doing that is that there are a bunch of interactive visualizations in each of these notebooks, and in order to see them, you have to run the code first to get all the data alive. Okay, so that is the first example running, and I have that on my own machine and have already run those, so you can see the visualizations. So as I say, there shouldn't really be any difference for those of you who are running on the Binder. The Binder is a public resource that just will fire up on demand, but you won't have much speed, and I'm not going to deal with that anymore. I'm going to close mine down. For those of you who do use Binder, bear in mind that it resets itself completely every time you use it. So each time, if you do something and want to save it, you have to download that notebook. All right, I'm going to leave that. Right, back to my presentation. The other resource that Quagmire has, of course, is a GitHub site. It's part of the Underworld family, so you can go to Underworld code/Quagmire. You can look at the original code there, and you can also open issues. We may need to do a little bit of work to make that completely open, which Ben and I will do after this webinar is over. So what about the surface evolution problem in general? Let me just give us a sort of a standard bit of background so we know roughly what we're all talking about. And so I will refer back, of course, to Romain's webinar that he gave, the previous webinar, the last one of 2018, which was about this problem. And I'm only going to sort of deal with the mathematical part of it, if you like. So what are the characteristics of the surface evolution problem? Well, basically, we are thinking about the surface evolution in this community generally as a rate of change of the surface height, a two-dimensional description of the height, which changes with time, and so that does imply certain things about multi-values and things that we are not going to be dealing with. The overall change in height comes from a number of different places. For example, the basement tectonics, a bunch of hill slope type processes, which often are modeled as some kind of nonlinear diffusion. That's the first time I've written on the right-hand side of this equation. And the second term is the non-local transport terms, which are most of those are to do with things like river runoff, where you have rainfall at one side of the domain propagating downstream along some complicated network and creating and eroding or depositing sediments and so forth. So that total runoff is an integral over a large area and is not like many of the other sort of terms that we often find in geodynamics type problems. So it requires some thought, and that's probably my contribution to this, is to provide some thought on how to implement those things. So this movie cartoon is a perfect demonstration of that. I'm not sure how well this will work for those of you watching live on Zoom, but basically in the cartoon version of this problem, you have a number of sources which are coming in as rainfall at the top of the movie, dribbling downstream. And actually, because there's three sources, eventually these three sources accumulate enough that there is a much stronger flow, and that flow is sufficient to turn the little Ferris wheel there if you put it in place. And if you only have one of those pathways, it doesn't actually turn the Ferris wheel. So it gives a good demonstration that it's the accumulated flow from a long distance away that's sensitive to the path that's taken, that you have to look at when you worry about the energy that's in a stream. So typically that does require you to aggregate information across a very large network. The network has some nice properties, that things flowing downhill generally aggregate. There aren't cycles, things, unless you have an Escher landscape, there's really not a way to build a cycle into it so that water continually flows downhill. It has to flow downhill and eventually out or into some sort of local minimum. And so there are many ways to do these algorithms, but they end up being some sort of way to traverse that graph that you can see that I've drawn here. So we're trying to calculate some sort of integral to calculate these power terms, some integral of the upstream area, and we can convert that into some sort of summation over the information that is upstream of any given point. We obviously have to calculate what that upstream is. As you can see from this diagram, the upstream nature of the problem can be a bit difficult in parallel, because in parallel, if you just randomly decompose your domain, the pathway of information can be quite complicated, and it can also be cyclic in that one processor can't finish until another processor finishes, but that other processor depends on the first one. And here is a contrived example, but it certainly demonstrates that rain flowing in at the very top of this sort of volcano will trickle down in a very complicated way through the processor configuration that I've drawn. And in general, it's not really possible to think of general ways to do these decompositions that completely eliminate all the difficulties. However, one can render all of these graph operations into matrix operations, and the matrix operations are completely equivalent, that as you pass information from one place to another in a matrix, you can see that, I'm sure if this actually is animated. Stuck. I don't know why that's not showing, but I'm just going to show the next slide. That the effect of moving information from one place to another in the graph is exactly equivalent to a simple single matrix multiplication, and the effect of transferring information from one point all the way to the very end of a tree like this that's in a graph form is to keep repeating that multiplication n times, where n is the length of the longest chain. So matrix multiplications on vectors of information are generally, if you like, a solved problem, and therefore we can say this is a solved problem. And then the only thing left to do is to implement it. So that's where Ben came in, actually. So I gave him the solved problem and asked him to implement it, and some scraps of code to show it worked. Here is an example of this is a place called Australia, and it has some interesting, it has some complicated river systems, but in general the river systems don't follow the domain decomposition that you might throw across some random triangulation of Australia. And so I apologize for people who are insensitive to shades of red, because I colored this all in sort of shades of Australian shades of red and brown. But here is a sort of a 20 or 30, I think, process decomposition of a triangulated mesh across Australia, and it's showing the river systems crossing those. This is a sort of a model of the river flows across that topography, assuming uniform rainfall, which we don't have, but we'll show you where the things might be. Okay, so let's think about some of the concepts of Quagmire itself. In order to produce images like I just showed you, we have to import some topography and create a mesh that can provide information about what the relative topographic gradients are. So what are the changes in height from one place to the next within a mesh, within the domain, but obviously meshing is one of the obvious ways to find it. We have two ways to do this: the triangulated meshes, which is what we'll concentrate on, but for at least potentially for efficiency, we also implemented a pixelated mesh class, which it should be able to use for regular rectangular meshes. And in principle, those are interchangeable classes, so everything that follows also works regardless of which your choice is underneath. But for the time being, we'll concentrate on the triangulated irregular meshes. Okay, so if we have a 2D mesh we have associated with it some mesh variables, and each point in that 2D mesh comes with a height location, and therefore you have the sort of image that I just grabbed here from one of the notebooks. Okay. Excuse me. So within Quagmire, we provide you some capabilities to generate simple meshes. And basically what that is, there's a few tools to create points that run across some boundary of some domain, a rectangular domain or an elliptical domain or something. And so we provide you with ways to do that, and then we provide strategies for importing that into a PETSI DM, which is the data management tools that we need. And as soon as we've done that, we can then create on top of that, we can create our own mesh, and our own mesh is the piece that is associated with all of the functionality of Quagmire. So it's a higher level object than just the data management. The mesh does things like having variables attached to it, which can then, which understand that they are small parallel collections of data, but for most of the time just behave like NumPy arrays. And so we take some basic point clouds, construct the PETSI DM, and from that we can make a mesh. We take our global mesh and we partition that then into a parallel mesh, which is a series of local domains. And associated with those local domains are also some overlapping shadow regions, which is a very standard way of dealing with distributed parallel information. So on the left-hand side of this slide is the idea of a largish mesh, which we're going to distribute over 4 processors. The 4 processors each own a certain number of nodes, but if you look at the boundaries between those meshes, you'll see that the triangulation that you would achieve if you just triangulated the points, say the orange points, is very different from the one you achieve underneath, which includes connections to the brown, red, and yellow points. So on the right-hand side, I've shown what happens if we introduce some shadow information, which is the overlap information between those domains. And there you can see that the connections between points are exactly the same, as long as we've taken those into account. So in other words, all the triangles that we produce, all the orange points are connected to the points they should be connected to. Not all the green points are, but that doesn't matter. Those are in the shadows. And that means that when we worry about things like who's downhill or uphill of which other point, that we really do have that information available to us correctly. So managing that shadow information is really what we put some work into making that vanish into our mesh variables. It's still important to understand that sometimes we can do the work for you when it comes to doing parallel stuff, but not every time. Sometimes you have to actually say, look, this is all the information I need. I want you to synchronize it now. And in our examples, we certainly provide those. So here is an example of some some mesh variables, which are really PETSI vectors, and they are consistent with the local mesh size, meaning the mesh that you see, including all of the shadow information. They expose all their underlying data as though they are NumPy arrays, but associated with them are some ideas of synchronization. So when you've changed the data, if it has made any changes in the shadow region, you probably should synchronize, either to throw that information away and update it from other processors, or to amalgamate it with other processors. This is a very typical sort of operation, and we just use standard PETSI operations underneath. Okay. We've tried to follow as well the Underworld mesh variable classes, which allow things like, if you've got a data distributed across a mesh, you should be able to obtain its gradient. You should be able to interpolate to points within there. And in Underworld, those things, the interpolation operation is called evaluate. It may involve other operations too, and there are gradient operations as well. So we try to reproduce those. If we go, we can have a quick look at some of this. Looking at the first examples that are in the notebook. So those of you who are following on Binder, you may have to restart because we've been waiting a little bit of time. But here is showing in the web browser on the right-hand side of the screen is the example of how to create structured and unstructured meshes. So we have some ways to do that, and we are visualizing these with Lava View as well, which you can interactively see in the notebooks and also interactively change on Binder. Doesn't matter. The structured and unstructured meshes have the same format to how we create them. But in one case, we have a series of quadrilaterals, and in the other case, we have a sort of a series of unstructured triangles. I'm not sure if this is going to work. Okay, so we can visualize these by pulling out some of the triangulation objects and visualizing them, and I would urge people to have a play with that on Binder later just to see what the purpose is. But this is really just a basic thing to get started on what the meshes look like. And the only other comment I will make is that when you do this in parallel, you don't want to try to create a 1 billion point mesh on your laptop or something and distribute it out. So the way that we do that is to create, first of all, a coarse mesh, which will be appearing momentarily in the there it is on the screen, and then we allow PETSI in parallel to refine that mesh. And PETSI has some inbuilt parallel mesh refinement tools that allow you to fill those pieces of information in, and then each of the pieces of that partition mesh will then be available on a different processor. And can then be used to populate the topography, either from some sort of function if you're doing an analytic kind of test experiment, or you can read that in from pieces of a DEM. Okay. If I go to the second example, in the second notebook example, then you can look at meshes which are topographic meshes, which introduces a whole bunch of extra functionality on top of that basic meshing toolkit. And some of the things, so when we build the mesh, it tells us all the things it's doing. It builds a triangulation, and it builds various things associated with the areas of the mesh. But it also builds all the neighbor information. And when we add a topographic component to that mesh, then we call this function, which is update the height, which is the synchronization function I've just highlighted. When we do that, it may not, yeah, there it's come through. Then it also calculates things like slopes, and it also calculates the downhill matrices that tell you how you can navigate uphill and downhill from any given point. That means that we now have access to topography, and therefore we have access to derivatives and hill slopes. So we can do that from various different methods. We also have a bunch of smoothing operators to eliminate some of the sort of errors that you might introduce through meshing, or at least it's an operator that you can use if you wish. Okay, and then this is sort of a typical example of what we use as a test mesh. We call it the, I'm not sure if it's going to update, we call this thing the crenellated sombrero, or also known as the octopus underpants model, because I'm sure that's what octopuses would wear if they wore underpants. And this thing is designed to be to have some characteristics, that it's got a, well, sometimes it has an 8-fold symmetry. But the point about it is that it's smooth in the center where that symmetry is lacking. So you expect to have uniform distribution if it rains in the center, flowing out through a number of sort of individual drainage channels. And it's a good test, actually, that we can then test that to see if these things produce the right sort of outputs. And this is sort of an indication of what the gradients look like. Okay, I'm just going to go back now and pick up on the I look at what's coming next. It's just goes straight to have a look at the surface process puzzle pieces. So our third example here in the meshing is to look at how surface process modeling works, and just like introducing this hierarchy of a mesh plus a topographic mesh, we also have a mesh that has sort of surface process features to it. So it has to be a topographic mesh, but on top of that, it has the idea that understands a bit about rainfall, and it understands a little bit about what the pieces of information it has to keep track of to calculate the stream power, and it has the amalgamation operations for computing things like stream power. So that's in the third example notebook. But again, rather than providing particular functions for calculating stream power, where there are some, well, there are many choices that can be made as to which exponents go into which piece of the equation. The thing that we do is to provide you with matrix operations that can accumulate flow across a mesh. And so, for example, we can create things like, we can take a mesh, we can give it a height, and then we can add to it the cumulative flow pattern of any particular mesh variable. Okay, when we do those kinds of things, we can then start to look at the difference between the slope and the cumulative rainfall, which I just switched over, and you can see how those rainfall patterns accumulate. And you can also see the difference between what happens when we introduce some smoothing to these kinds of stream power functions versus of various different natures. Okay, but we don't like to consider that any one of these methods is better, but it's horses for courses depending on what you're working on. And at the end of this notebook, we've sort of demonstrated that despite the fact that everything is mathematically quite smooth, and therefore each of these catchments should capture the same amount of outflow, the meshing itself, the triangulation, introduces enough irregularity into the problem that we actually, although we conserve total output, it's not evenly distributed. In fact, some catchments miss quite badly in this case. Okay. So those are useful pieces of information. I'm going to go switch to back to the theory part and just quickly fill in some of what we need to just cover the next couple of notebooks. So in the matrix approach, there are also some other tools that we can make use of, and the first of those, which I'll talk about later, is actually the fact that if we can propagate information downhill, then the transpose of that operation is to propagate it uphill. And although that's not a one-to-one mapping, it's exactly the same process. And so we will be making use of that in a moment to propagate information from the outflow points back up into the catchments. The other thing that we can do very easily is that we can pass information not just to the nearest downhill neighbor, but to maybe the second nearest downhill neighbor as well. And we could make that dependent on gradient or on height difference. We could introduce further downhill neighbors. And D1 and D2 are both very sparse matrices, just like they are in fact equivalent to the identity matrix in terms of their information density. And so, this produces a further. It's still a sparse matrix when we add the two together. So actually, we're introducing the sort of this idea of multiple downhill pathways, which I'll show you how it works in a moment, with a very little extra cost. Okay, so for us, that's a question of providing more functionality. Half the papers dealing with regular meshes. As the sort of underlying process would tell you, that actually the only way to eliminate a lot of the staircase type river mesh dependency is to introduce multiple downhill pathways. But it's also true for regions which are very flat, where actually there really is a sort of, there really isn't an obvious channel where material where flow is being passed from one point to the next. We can create an overall flow matrix that has a much greater path, has more than just a simple tree traversal built into it, but is based on that. And actually, my last point on the slide is that the transpose of that matrix also runs information uphill in the exact same way, although it doesn't exactly define a catchment as it once did. Here are some examples of that, and I showed some pictures in which I pointed out the fact that even if we have uniform rainfall on a mesh that's very mathematically symmetric, we get a picture like the one in A here, which is looks very much like the rivers on a map, but unfortunately is not really capturing. I mean, what you're seeing there is a meshing error, or meshing sensitivity, that the pathways are really dependent on the fact that some triangles are slightly larger than others and so forth, and that effect amplifies very quickly. And some of those catchments are outlined down below in B, and you can see they're not all of equal area, and there really is interesting knock-on effect of this irregular triangulation. Same would be true of a regular triangulation, I think, for a mesh like this. If we introduce multiple pathways, then that process, then that mesh sensitivity becomes less important. And in C, we have 2 pathways, and in E, we have 3 pathways available to the flow. As you can see from D and F here, those catchments are now a little bit fuzzy. The water that arrives at the end of one of these channels has come from other, what we would classically call catchments. But it's in a fuzzy way, and they have a much more, their area is actually much more reminiscent of mathematically what the surface looks like. And it may not be very visible. I can see it, and I can see that it's come through okay in the screencast here. But I'm happy to distribute the PDF of this talk, and you can see quite clearly what those pathways are. And I just wanted to show then that if we go to the next example notebook, where we implement this thing with multiple downhill pathways, there really is very little that we have to do that's different. So when people go through, when you go through and have a look at what we're doing here, I'm going to run this one so that the visualizations come up. Now, when we look at what we're doing here, it's the same sort of process. We build the mesh, but we specify that we're going to build multiple downhill neighbors for that mesh, and then we use those to calculate. What the flow is going to look like. And so to wait for this whole thing to finish, then we can start to look at the differences. So in the notebook in what's showing now on the screen, there are examples of calculating the stream power with 1 nearest neighbor, 2 nearest neighbors, and 3 nearest neighbors built into that system. So I'm not telling you that one of these is better, but I am saying that if you feel the need to introduce this into your code, all you have to do basically is apply a slightly different argument when you develop the mesh and tell it which of these operators you would like to use, and you can change that on the fly as well. So this is then a replotting of the this graph below, directly below, is a replotting of the flow pathways and showing how they reach the catchments, and the irregularities are considerably reduced in that process. The last part of this is a discussion of computational efficiency, which I don't think is of we particularly need to cover at this point. I'd rather talk about that in a discussion if people would like to. And so the last thing that I really would like to cover as part of the tutorial here, or the discussion here, is to talk about what happens when we go to real landscapes. And we'll be in example 5, where I killed the kernel doing something, unfortunately. So I'm not sure. But I'll talk about the theory behind this first of all. So one of the issues associated with just taking a raw elevation model and putting triangles across it is that, well, for starters, there are some errors in that model, just associated with the measurements. But the other thing about it is that there is a triangulation error, which we already saw. Even if we have a perfectly resolved topography, as we had in the mathematical examples, we don't always get flow in the direction we expect, because sometimes, by virtue of the triangulation, a sample point will miss the middle of a channel, for example, and it looks like the channel stops. This example here is taken from a digital elevation model, and exactly that problem is visible in a low resolution meshing, which is appropriate to the data that we got. It's not possible to follow every channel all the way down. We don't always know. So we could do two things about that. We could try to find the channels with the mesh points. The other thing that we can do is just simply to let the channels flood up and spill over. So like a sort of mini artificial dam has formed that's a few centimeters high, and we're actually just going to say, I'll let the water run over it. Okay. The other thing is, of course, that the rivers in these systems are flat, and we don't see the riverbeds. And so if we're trying to work out where the rivers are to calculate the flow, we may need additional information. And that's part of this sort of whole thing. So built into our Quagmire algorithms is a filling-the-swamp type algorithm, in which we've taken our sombrero landscape, and basically it looks like a road sign out in the desert. Someone's taken a shotgun to it and put lots of dents in it. So it's a horribly cratered landscape. So what do we do in those circumstances? Well, this could be a real landscape. There's nothing wrong with that. What we want to do is find out where all those hollows fill up and where they spill out to. And so on the left is the horribly cratered landscape. On the right of this is what happens if you actually find out where all the holes are and let them fill up with water, and then look at the flow afterwards. Okay. So we provide a number of different bits of functionality. This one that sort of is lakes and swamps, which just really tries to find the hollows. We can also just try to find the little small dents that are there by virtue of meshing errors, and they can be filled separately. And again, this tends to be something that one would want to do by eye, because real landscapes often have lakes, and it's not appropriate. And some of them have internal drainages, like Australia, where it's not appropriate to try and fill it up by hundreds of meters to find where it goes out to the ocean. And this is really something that we don't think there's a general algorithm for, so we give you bits and pieces to make that. As an example, many people may have seen before, where tilted egg box or tilted waffle, that we have to fill it up first to find out where the next, where the flow goes next. And so this is the result of applying that swamp filling algorithm to the previous landscape that I showed. And this is typically a few centimeters change in height that's required to connect the channels. So this is the green here is how much height change we have to put in, and this is the landscape with all those channels then connected. Whether or not this is more realistic is really not the point, actually. This is a toolkit for allowing you to do this kind of operation, and it would be especially important on synthetic landscapes. And here's the original Australia landscape. We try and connect things up. Australia does not look like this. It doesn't have enough rain to get these kinds of connections. But in Australia, we don't have good information about where the rivers flow necessarily, because they often flow in ancient channels that are sediment filled. They're not that full. So being able to do this kind of process is useful to be able to continue to track information, even though even though there may be there may not be obvious where that pathway to get the stuff out really exists. So there is an example for doing this pre-processing, which again I'm not really going to go into a great deal of detail on that, but it shows how we take the original mesh, we simply rebuild, so this is a repetitive process, and then actually artificially add a bunch of low points and dents and things into the landscape. And then there is an operator here to go back through. I think I killed this one, and it certainly dies on. It's certainly too much for the binder instance at the moment, so we may go and have to fix this. But you can see by looking at this, it's a way to visualize where the slopes are and where the lakes are, and you can see those individually visualized in this notebook when we go through it. So I feel like we're sort of coming to an end. I wanted to have one sort of conversation briefly before going back to this about how we do well, two more aspects of this. One is the last of the functionality for identifying catchments, which is really related to what I just talked about, and then the final thing I'll talk about is how we look at developing a proper landscape evolution code. So finding catchments, this is where we basically take the same operations as we were previously talking about, the downhill matrix operation that moves information from one node downhill and applied sequentially moves it from all nodes in a catchment down to their outflow point or down to their local minimum, so local minimum in the mesh if we've got an internal drainage. So we need to. So if we look at what those drainages are, the outflow points of this particular mesh, once the lakes are all full, then everything flows in a fairly organized pattern down to the lowest points around the brim of the hat. Okay, and there are 1, 2, 3, 4, 5, 6, 7, 8 of those, I think. And if we locate where those points are, there's a function for doing that. Then we can take that and we can provide a unique identifier for each of those points and propagate it back upstream. So we propagate the ID of each of those outflow points back. And if we do that on a single, if we use a single neighbor algorithm, then that is a unique pathway back up. And you can see how that finds all of the appropriate places, all the appropriate divides between the catchments in this particular mesh. Okay, in order to build that, there is an example. The example numbering is a bit messed up in the notebooks versus the naming, but so this shows you how to do a catchment analysis using the transpose of the matrix. Again, when I tried to run this earlier, it overflowed binder, so we'll sort that out and let people know once it's all working. But the uphill propagation operator is almost exactly the same as the downhill propagation, but it doesn't actually sum information, it just passes it upwards. And that's because it's almost exclusively used for this kind of operation where we want to know, suppose we have a catchment, how do we identify it? Or suppose we block a stream with a dam, how do we propagate the height of that dam back upstream to see how high it fills? Okay. Okay, so that is in the final notebook. I can't reach with my mouse. Oh. And in that final notebook, we show you how to identify, how to first of all just go through the same process of pre-processing the landscape and identifying everything, and then finally how you visualize the catchment information in a number of different ways, with a whole bunch of different things to visualize on that last snapshot, or that that last visualization, lava view visualization, which I won't attempt to go through because it'll take too long to run. Okay. So before we open up for discussion, I wanted to point out how we view the whole landscape evolution process. I haven't really put this in the tutorial, although this is there for future, sort of very near future reference. Basically, we provided operators. We provide gradient operators. We provide downhill operators. We provide cumulative downhill operators, and those are what's needed to solve the equations at hand. Because we can't find this, there's really not a community agreement on which of those things have to be composed in which way. So we haven't made any attempt really to put these together into a preferred model. And as a result, we haven't really provided any templates. So there is an example hiding in the Docker and on Binder, which is called erosion and deposition. And that just shows you how to go through and build various different model. I'll show you. Shall I show them where it is? Okay, when you want to find your way around in Binder, just like anywhere else, you go back to the original Jupyter homepage, and you'll find where our notebooks are. Okay, they're under notebooks. There's one called Landscape Evolution, and within there's one called Erosion, Deposition, and Time Stepping. There are different approaches to doing this, in which the sediment balance and the sort of balance between stream power, sediment load, and erosion sort of all composed differently, and especially for how you handle deposition. All right, and we coded 3 common ones up here to show how that works. And we've shown you what the equations are for each of those, and we've also put together a big time stepping routine that tries to pick one of those and do something with it. Okay. So that's where this starts to look like a real code now. And I think we should probably not try to go through and show you what all the pieces of a real code look like, but leave that for later. And let's just talk briefly about where we are trying to go. Okay, so then I'm just reiterating our goals to provide a grab bag of efficiently implemented Python classes for landscape evolution models. And sort of, I think what we focused on a bit more at the moment is the analysis side of this. How do you deal with landscapes that are given to you? I haven't really talked at all about how we do examples in parallel, and that's mostly because we focused on notebooks running in the cloud where we don't have a lot of parallel resources. But everything that we've described works with very little modification in parallel, including the visualization, though not the interactive part of that. We've introduced a mesh variable class, which we described to you. There are some additions to that. Mesh variable stuff is changing quite fast, and we're trying to make it look a lot more like Underworld mesh variables. So some of those mean that we have to be able to return vector variables, not just scalars. For example, to do gradients properly. We haven't really used mesh variables. We've interchanged the use of mesh variables and NumPy arrays, and that's probably a little bit dangerous in parallel. So we were going to make this the mesh variables more primal in that sense, and the mesh variables as a result need to be able to support mathematical operations. So they need to basically act like NumPy arrays, that you can add them and multiply them and so forth. Another important thing that we do in Underworld, which we haven't really dealt with here, is using is real units and scaling. And Pint is a Python package we use in Underworld do that, and we would use that same thing to build units into the mesh variables. Another thing that's obvious that we should do is to introduce templates for those time-dependent terms, so that we can eliminate some of the potential numerical difficulties of time-stepping those equations. And we actually have to try to work out if that can be generalized before we can really do that. And it does require us to have some sort of callbacks or Underworld type functions to be able to let people still do whatever they want with the with which equation systems, which pieces of the equations are defined in which way. So we may also improve the high-level interface for novices, and if we do that, it looks like we're setting ourselves up for another webinar in the not too distant future. So I would like to, I realize I've run over time a little bit from the point of view of handling questions, so I would like to open it up to questions at this point for myself or Ben. And please bear in mind that we're both sat in the same room, and it is an echoey room, so we may want to be, muting each other and stuff like that as part of this process.
Great, thank you, Louis. That was a wonderful webinar and tour through Quagmire. It's clearly a lot of work that both you and Ben have put into both the code and to making it available in the Jupyter Notebook. I'm looking at your repo, and I'm noticing, I was wondering what the licensing of the code is, and if people wanted to contribute, how they could do that. And the third part of the question is, if they actually use the code, is there a release or any other publications in the work that they can cite?
Well, I can answer bits of that. I've forgotten what the first one was. It was, what is the license type and contribution? So the license is, it'll be the same as the Underworld license, I think, is predominantly LGPL. So if this is something we just have to tidy up. Yes, we would accept contributions, again, similar to Underworld. There's sort of, we're growing our own internal development group. It's just been Ben and myself as a side project for a while. We do have, so we would accept pull requests for that, and we'd also accept, well, actually, I say advice, but we'll accept conversations about how to implement some of these, the best mechanisms for implementing some of these things like mesh variables. We are trying to keep in lockstep, if we can, with some of the Underworld developments. That includes the fact that this is mostly Python 3, and that PETSI is not really Python 3 right now, so it's a little bit complicated, and that's why we recommend using Docker for things. So there's be some things coming through from people about that would be quite complicated. And then in terms of publication, well, first of all, we would, I think it's not on Zenodo at the moment, but it should be. The StriPy, people are interested in StriPy, the sort of the meshing part of this whole project, that is on Zenodo already, and is this, excuse me, is installable through pip already. And we're in the process of writing up, excuse me, in process of writing up the algorithm side of this for people to cite that.
Okay, thank you. Are there any questions out there? Just please go ahead, either turn on your mic or type something in the chat. While people are preparing their questions, I'd just like to reminder our next webinar is actually in 2 weeks. It's February the 14th at 2 p.m. It'll feature Enzo Choi from the University of Memphis and Tanu Malik from DePaul University, and they'll talk about conducting reproducible science with psi units. So as a reminder, the link is in the announcement emails for the binder as well as in the chat, and it'll also be posted with, I believe I'm going to get a copy of the presentation from Louis. We posted with that on our CIG website shortly. Well, I don't see any activity, any questions out there. So I want to thank both you and Ben. Whoops, here we go. Robert, can Quagmire handle spherical meshes? You're muted, Louis.
Sorry, I couldn't move the mouse fast enough to get to the unmute bit. Can it handle spherical meshes? So the answer is yes, in prototype form, and actually this is one of the things that'd be interesting. So StriPy is a spherical meshing. It starts out as a meshing on the surface of a sphere, geographical sense, although it works in radians. So it does understand the notion of the spherical meshing, but at the moment we have kind of sidestepped that and said it's just meshes. So this is something where to build the full, so Ben, you did build a full spherical meshing example.
Yes. Am I audible?
Yeah.
Yeah, okay. Yeah, so I guess for the spherical mesh class, it'll be handled as Louis says, like all the rest of the classes. So we've got the triangular mesh in Cartesian coordinates. We've got the Pix mesh, which is just a regular grid. Then the spherical mesh will be part of that group, and that should be transparent for the rest of the functions and calls that we make for the higher level mesh classes that control the topography and also the surface process algorithms that have been implemented.
Yeah, so that was a little bit echoey, but okay, yeah, there was a little bit of an echo there, but the answer was the answer that is yes, it can, and it would be hidden basically as so we've convinced it to do it already, but probably we would produce a third mesh class that would just be interchangeable, which would be one which was more geographically related. So rather than just being spherical meshes, which you could kind of pass through at the moment, it would actually be sort of geographical meshes. So you would read in things which knew about latitude and longitude and their height.
Great. Any more questions out there? Going once, going twice. John Mansour, do you have any results for parallel scaling efficiency?
Yes, we do have results for parallel scaling efficiency, which actually I think are pretty, well, Ben did most of these and we ran them up to, tell me how many processes we ran them up to? Thousands or something?
Yeah, about 1,000.
Yeah. So we ran up to about 1,000 processes, and we had pretty good success. So there's an echo there. So pretty good success for everything matrix based on the PETSI stuff, and everything that's just basically simple decomposition. And then we had a couple of there are a couple of issues associated with not just the parallel part of this, but this is not none of the algorithms out there are order n. So there are some issues with just going to higher point densities. So doing the weak scaling kind of results, we found that there's a dependency which results in longer flow paths, which introduces a dependent which makes things a bit interesting. But basically, it's looking pretty good in terms of how we export everything down to PET-C, that it's handling things reasonably well. And then we have this other little trick, which is pre-multiplying out the matrices to densify the matrix. And that's not particularly complicated. There's an example actually in the notebooks, and that does introduce sort of a tunability in terms of how you approach particular architecture. And that I think will help us with getting communication down a bit, or at least getting the communication memory CPU type balance across different machines. So we haven't got that. That's for the publication.